Thank you so much. Yeah, and thanks everyone for being here. Yes, so I'll be talking about a paper on optimal staffing with interdependent values. And this is joint work with my wonderful co-authors, Mauras, who's right there, and Rebecca Reiffenhäuser. Okay. So obviously, I want to start with some motivation. If this works. Okay. We are in the online algorithm session, so you know what's happening. We want to make decisions online. So we see a sequence of options, right? Let's say I have an item to sell, and I see a sequence of buyers who come one after the other with their bids. And the decision that I'm faced with is, should I select the current option, the current buyer, or I reject them and let them go forever so that I can wait and gamble for something better in the future, right? So I want to design good online algorithms that can compete well with the hindsight output. But in many of these settings, including when I want to sell this item, we are faced with an additional challenge. And that is of interdependent values. Because if I'm trying to sell this painting, let's say, and you are the buyers here, I want to ask you, what is your value for this art? Just think about that. But now, what if I tell you that this is actually a Picasso? I bet for most of us here, this would have really changed our values, like from maybe $10 to hundreds and thousands of dollars, right? So the point here is that we are faced with this additional challenge where the agents, when they arrive, they may not even know their own value a priori because their values depend on others' private information, right? So we have both this partial information setting that's coming from interdependence between agents' values. And this is exactly the two challenges that we are going to see together, both the online arrival challenge and the interdependent values. So the question we are faced with is, given a sequence of n interdependent values arriving online, where upon arrival of each value, I have to decide whether to accept and stop the process or irrevocably reject them and continue and see the next case, right? And the goal here is to, of course, maximize the value of the accepted option. Okay, so to formally study interdependence, we turn to the elevated model of Milgram and Weber, who built upon also work of Wilson, and they won the 2020 Economics Nobel Prize in part for this contribution. So in the interdependent values model, again, we are in a single item setting with n agents. Each agent I has a private signal Si. So this can be whether the painting is a Picasso or not, or their information about the item, or even how much they personally like the item, right? And the agent also has a valuation function, Vi, that aggregates the signals of all the agents to a value for the item. So Vi of S1 through Sn is the value of agent I. We can think of the valuation functions as known and being monotone in all agents' signals. For example, you can think of the resale model for the when we think about art auctions, the value of agent I depends both on his value. So you can think of Si as being how much he likes the item, and this being a weighted sum of how much other people like the item. This and captures the potential resale potential of the item, right? And this whole thing dictates what the value for the item is. Right. So in our model, we are going to look at both the online algorithms with this specific interdependent values model. So we see a sequence of n agents with interdependent values arriving online, where upon arrival, agent I is going to reveal her private signal, right? So agent I arrives and shows us what her signal Si is. And you can think of the valuation functions are all publicly known and known beforehand. Okay? And in our work, we consider both the profit setting and the secretary setting. So in the profit setting, the signals are going to be drawn independently from a known prior distribution. So we know the distributions D1 through Dn. And when agent I arrives, her signal Si is drawn from distribution Di, independently of other agents. but the arrival order is going to be some worst case adversarial order. Okay? On the other hand, in the secretary setting, the signals are going to be arbitrary. There's no prior information or any assumptions on it. It's going to be adversarially chosen. But the arrival order is going to be uniformly at random. And our goal here in both is to compete with the offline optimal, like the expected max value of the agent. Okay? So I'm also going to make one more final assumption or restriction, which is that the valuations come from a class of functions called subadditive over signals. It turns out that this is a really crucial assumption, but let me first define what that is. A valuation function V is subadditive over signals if for any partition of the agents into X and complement of X, the value of the values on all agent signals S1 through Sn is going to be less than the value only when we look at agents in when we look at agents in X and zero out the others, plus the values when we only look at the agents not in X and we zero out the rest. Okay? So the value on the whole set is going to be smaller than the sum of the values of its parts. And this is actually like the most general class of valuation functions where the signals are not complements. When two people come and say that it's a Picasso, your value is not like really going up twice as much as when you only hear from each of them separately. Okay? And as I said, this is actually a really crucial assumption for us because without the assumption that the signals are not complements, we can have really strong impossibility results where no non-trivial guarantees can be given, which is not really surprising because even in the offline setting with options with interdependent values, we kind of need assumptions such as submodularity over signals, which is a strictly subset of subadditive weighers, where this assumption of submodularity has been very crucial in providing approximation guarantees in the offline setting as well. Okay, so just to recap, this is going to be our model. We'll have each person will arrive online and reveal their private signal SI, but we know the valuation functions of everyone beforehand, and the valuation functions are going to be subadditive over the signals. Yeah.
When you talk about subadditive signals, are you assuming that if a signal is zero, you haven't seen it yet?
You can, yeah. So you can think of it as if the signal is zero, we haven't seen it yet, because I'm assuming monotonicity. You want to think of it as this is the worst possible value I can have given the signals that I've seen so far. That's one way to think. Yeah. Thank you. Good. But so as I said, our work looks at both the profit and secretary setting. But in this talk, I'm going to really focus mostly on the profit setting. But if you want to talk more about the secretary algorithm, come find us, and we'll be happy to share. Okay. So right. So I'm going to start with some bad news in the profit setting. So it turns out, in the case of the profit setting, when we have subadditive valuations, but we are not making any other assumptions, no online algorithm can get better than an omega n approximation. Right? I can show you a simple hard instance that where the optimal is at least an n factor better than any online algorithm. Okay, and I'm going to do this actually just in this one slide. It's a very, very simple instance. I hope I'm going to convince you in 1 minute. So the main idea here is that the adversary who chooses the order can hide the most informative signal at the end. Okay, so in our setting, only signal. Okay, in our setting, only the signal of the last agent Sn is going to be of any use, and that's going to come from interval 0, 1. And I don't care about S1 through Sn minus 1. You can think of them as 0 or anything you want to think of them. So the valuation function of each agent I. Yeah. So the valuation function of each agent I is going to be, I cannot, all right. It's going to be 2 to the I. It's going to be something non-zero only when Sn is greater than 1 minus 1 over 2 to the I. Okay, so agent I's value is going to be 0 when Sn is smaller than 1 over 2 to the I. And it's going to be equal to 2 to the I when Sn is greater than 1 minus 1 over 2 to the I. So the expected value from any agent is actually just 1, right? But if you look at the true underlying values for any signal realization of Sn, they are going to be powers of 2 squares so long up to like 2 to the k, and suddenly it's going to become zeros. But any online algorithm, like we have to make the decisions online, and we are only going to see a bunch of zeros. Up until the very end, only when we see Sn, we are going to learn anything at all. Up until then, we are only going to be seeing zeros. So all we can do is like guess where to stop. But as I said, no matter who you decide to choose, their expected value is just going to be 1. Okay? But the opt here can get an order n, like up to like n over 2. Here when you know the signal realization and can exactly go and choose the highest 2 to the k for each signal realization. Okay? So no online algorithm here can do better than basically 1, but the opt can get a factor n higher. So this impossibility result actually like really like forces us to like make two distinct forces us to see the agent's assumptions more closely and look at like two distinct cases of myopic and far-sighted agents. So the instance that we saw where the agent's signal actually depended on someone on the future, like they didn't even arrive, agent n didn't even arrive, but my value very crucially actually depended on them. So here we call them far-sighted agents. So their value can depend on all the agent's signals, including the people who haven't arrived so far. This makes sense when we think of the item as some long-term investment. So obviously we are thinking about the future benefit. But there are many settings where it makes sense to think about agents who are myopic. So we have an auction that's online. They come, either they leave the auction and they go away, or they get the item and the auction stops. So their value for the item basically only depends on the signal that they've seen right now. So this is what we call myopic agents, where their valuation function is defined only as being dependent on the signals S1 through Si. For each agent I, they only see the past signals S1 through Si. And their valuation only depends on this. And it turns out when we make this assumption and look back at our profit setting, we can actually get very nice positive results. I'll kind of talk about all of the boxes in a second, but I'll take a quick second to like add a little bit about the secretary setting, which I'm not going to talk about later, is that this distinction between far-sight and myopic completely disappears in the secretary setting. This is because of the random arrival order of the agents. Like I'm going to see a random subset of agents in the past. So that actually gives me a good estimate of what the value will be on the whole set. So in the secretary setting, it turns out we don't need to worry about far-sighted and myopic. But in the profit setting, we are going to see that like, even though in the far-sighted agent setting, we can't do anything better than omega n, when the agents are all myopic, we can actually guarantee a constant factor approximation to the offline optimal. Okay, and that's what we're going to look at closely right now. Any questions about the model so far? Okay, so yeah.
Is there any extra randomness in the evaluation besides the randomness in the signals?
No, so we are fixing the values. Values are not coming from any sort of prior. I'm assuming some known instance where the valuation functions are fixed. Yeah. Okay. So again, so the main like positive theorem is that like in the profit setting with myopic agents, a simple online algorithm can get a 4 approximation to the expected offline output. Okay. And this is really a simple algorithm that builds upon like the classic threshold algorithm for profits that probably most of you know. So I'm going to define a threshold that is equal to half of the expected optimal, right? And then I'm going to look at the first time t such that the value at time t, Vt, is going to be greater than the threshold x. But I'm also going to make a second check and only then accept The check is that if someone is obviously better than me in the future, I should not actually settle for this item. In particular, I'm going to actually use the interdependencies to our benefit. I'm going to look at the signals so far, S1 through ST, and use this and compute the future agent signals. They might have better values actually, but like let's only look at the signals that we know so far. Even with these signals, if someone is obviously better, we shouldn't accept the current option and we should wait. So the algorithm is going to check whether at each step they satisfy both these conditions. That is, you have to be better than the threshold, and you have to make sure that like your current value is greater than every other agent in the future, only using the current information. Okay? And I want to like maybe give a very, very high level like proof sketch, not even a sketch, just an intuition of like how we actually go about proving this. So the main thing we want to do is to compare the agent that the algorithm accepts, who is at time t, bt, and compare the optimal agent, the agent who has the highest value, like when we look at everybody. And note that whenever the algorithm stops, it has to be the case that we stop before we see the optimal agent. And this can be shown mainly by looking at the second case, right? Like the optimal agent will always satisfy the second stopping condition. So if anybody is going to satisfy the first condition, which is that their value is greater than x, obviously the optimal agent's value is also going to be greater than x. So we wouldn't reject the optimal agent. The algorithm is going to stop at some agent, right? But if the algorithm doesn't stop, that means that the optimal agent did not have a value greater than the threshold, like their value was strictly less than the threshold. In fact, every agent's value is strictly less than the threshold. We're just going to use these two observations along with the fact that the valuation functions are subadditive. So I'm going to consider the value of agent I into like three different terms. The first term is just when the algorithm doesn't stop, it's their value. The second and third terms are just using subadditivity and partitioning the signal set into before time t and after time t. Okay? And using these two observations, we are able to like very easily bound the first and second term. Because when the algorithm doesn't stop, we just said that like nobody's value is greater than the threshold, so I can bound it by x. And when the algorithm does stop, when t is less than infinity, we know that whoever we actually ended up accepting has to have a value greater than all the future agents' value using just signals S1 through ST, right? Like the second stopping condition. So using that, these two things, and also with not that much effort, we can bound the third term in expectation using the independence between the signals we've seen so far and the signals we have not even seen when we stop. We are able to like do a little bit more algebra that I'm not going to show you, and show that like we can bound the expected value of the algorithm by 1/4 times the expected value of the option. Okay? So that is our main positive result. And so I want to quickly also talk about the strategic agents a little bit. Like as you see, like without the setting of non-strategic agents, both in the Prophet with myopic and the secretary setting, our bounds are exactly 2 away from the classic bounds of 2 and 3. And in the strategic agent settings where we are forced to also think about truthfulness, we lose an additional factor of 2. So when since the agents have to reveal their signals, reveal their private signals, we need to think about how to incentivize them with a truthful mechanism so that they will reveal the signal truthfully. And it turns out that only thing we need to worry about is whether the allocation probability, the probability that we actually accept the agent, is monotone in the signals, monotonely increasing in the signal SI. But the Prophet algorithm here, even though the threshold started, the check where we check whether we are above the threshold is monotone, the second check is actually not monotone. Because when I increase my signal, maybe someone else really, really values that it's a Picasso and their value increases way more compared to mine, right? So we deal with this by like separating these two things with the use of randomness. I'm not gonna maybe talk too much about it, but feel free to like ask me about this offline. Yeah. So with that, I'm gonna just wrap up flashing the result and also like tell you that like there's a lot of open problems here. Just like take your favorite profit secretary problem, like look at all the great talks that we've been seeing on profits and secretary and online algorithms, and just think about what will happen if we can use interdependence here as well. So thank you so much for listening.